So hello everybody. So this is a shorter video that I'm recording instead of your giving a live lecture in the class. The reason for this is that we have our quiz on Tuesday. So instead of like having a quiz and having a lecture, I'm trying to kind of have like a 30, 45 minutes ish lecture recorded here so that you can watch it so that we can then continue the class on Thursday. Please make sure to watch this before coming to the class on Thursday. Okay. So what's the plan for today? So far let me see if my for some reason my pen doesn't work. Yes, okay. All right, sorry about that. So far we talked about design of the processor with data pathway controller. Then we discussed how we can improve this using pipelines. And we kind of talk about various different things. So 4 major things that we talked about in order to improve our baseline single cycle design. The first thing we described was pipelining. We showed that how pipelining can improve the performance by essentially improving your CPI. Then we talked about forwarding to kind of prevent the stalls. Then we talked about control flow hazards and speculation to again kind of avoid stalls. And then finally we talked about kind of dynamic branch prediction and making decisions based on taken, not taken, and so on and so forth in order to even further improve the performance, right? So this is kind of like these like the high-end processor with all these features in order to improve this. We also kind of like very short for briefly talked about the impact of the compiler and software, but mainly we are focusing on what we can do in the hardware to kind of improve this, right? So now with all these features, the question is, can we kind of improve our processor even further? Like what we can do in order to kind of make this even faster systems. So we kind of like going back to the same questions that we keep asking in the past 2-3 weeks, and that is, can we do better? Okay. So if you think about various different options that we had this iron law, which was the CPU time was equal to IC, CT, and CPI, right? So essentially, if I want to kind of reduce this, I need to reduce all or some of these 3 metrics, right? So let's kind of like explore what are the options that we have in order to improve our system. So essentially the idea is that can I decrease the CPU time? Okay. So the first thing that comes into the mind, and we kind of discussed this in the class before as well, is how about adding more pipeline stages? Because adding more pipeline stages has various different benefits. For example, it can reduce the CT and it keeps the same CPI, right? So and then IC doesn't really change. We talked about this, as I said before, that this is true, and that's what we did in the class as well, to start adding 5-stage pipeline. But what we're going to have at some point is that what we call a diminishing returns. Essentially, we're adding 3 things that's kind of like negatively impact our processors. The first thing is we're essentially by adding more and more pipeline stages, you're adding more and more hazards, because for example, remember that we had hazard between write back and EX. Now if I have multiple stages between these two, then the hazards are even more. Every 2 kind of components, every pair now has potentially a hazard, right? So my forwarding logic gets significantly more complicated, my stalling logic gets significantly more complicated, and so on and so forth. So at some point, this too much complexity will be added to my system that negatively impacts the overall design of my system. And remember that we always wanted to have kind of like delay between pipeline stages, that we wanted to be the same. But if you're adding more and more complex things, for example, to your decode, at some point this will have a negative impact on our overall clock cycle. So it's short, kind of summary is that pipelining can help, and in fact, that's what we do. But at some point, some pipelining will no longer help us because it was just adding too much complexity to our systems due to the hazards or additional delays because of reading and writing the registers, and that it no longer is helpful, because now the CT actually doesn't go down, it actually goes up, which is the opposite of what we want. Okay, so we kind of like hitting the limit in terms of pipeline stages. Okay, so adding more pipeline stages or changing the pipeline stages won't help. Okay, so let's see what else can we do. So if you think about this, that pipeline stages is really what we are going after. It's because of we are basically doing this what we call scalar pipeline, which means that we are really processing one data at a time. If you remember, we kind of started this idea with a single cycle design, right? So in single cycle, we said that we feed one instruction into the design and wait for this to finish, and then we feed another instruction and another instruction and so on. So one instruction at a time, right? Then we saw this thing that's saying that, okay, why are we doing this? Let's actually divide the processor into pipeline stages, and then let's feed one here and another here and another here and another here and another here. So essentially these 5 will be independent from each other, and this way we can kind of have an overlap. Okay, but if you can see this, like if you look at this, for each given stage, so for this stage or this stage or this stage, any of the 5 stages that we have, we're only processing one instruction at a time. Okay, so in other words, at best what we can do is that we can at best achieve IPC equal to 1. We cannot go above IPC equal to 1. And in reality, actually, IPC is much, much less than 1. Why? Because we have all those stalls and hazards and all those things. So our effective IPC is less than 1. In other words, our CPI is more than 1. There are more than one cycle to finish one instruction. Okay, so it's really what we are left with is improving the CPI, because CT, because CPI cannot really be improved, and we cannot really add more pipeline stages or anything like that. So it's really the only thing that we can do is improving CT, right? And CT itself, as I said before, is usually just it's a function of technology, right? And we really don't have much kind of flexibility at the architecture level to change CT. So if the faster transistor comes, we can increase CT. So there's nothing that we can do really at the architecture level that we can improve CT. Okay, so given this, and then I told you before that IC is really at the software level or compiler level that's kind of being improved. So nothing can be done for the IC itself, right? So at best, so basically, kind of like status quo is, at best we can achieve CPI equal to 1. IC is not controlled by us, and then the CT is also just a function of technology, right? This is basically the end of the story of scalar pipeline systems, right? You cannot really go beyond this, okay? And all these techniques that we showed you, that like, pipelining and branch prediction and so on and so forth, at best can give us IPC equal to 1, okay? So in order to kind of like achieve significantly more speed up, we need to do something radically different, all right? So in order to answer this question of how to improve the performance, we basically need to kind of, as I said, look at this problem differently and say, okay, so far we have this pipeline stages, and what we are doing is that we are kind of running one instruction at the time of each, although these are different instructions, but in each pipeline stage we only have one instruction, okay? Now what I'm suggesting is that how about we actually do 2 at a time? So essentially kind of like replicating this pipeline stages into multiple, let's say 4. And then what we can do is that if we can run like 4 of these at the same time, then potentially I can have 4 times faster processor, right? So kind of like parallelize at the pipeline stage level, okay? So we call this what we call the instruction level parallelism, or ILP. right? They were basically like running instruction in parallel at different stages. So this is one stage, let's say this is fetch. So what we're suggesting is that instead of fetching one instruction at a time, what about fetching 4 instructions at a time? Then in that case, you also need to kind of keep the pace. So you decode 4 instructions at a time, you execute 4 at a time, and so on and so forth. So if you can kind of do 4, 4, 4, essentially at each given clock cycle, what we're going to have is that we're going to execute 4 instructions. So our CPI is actually 1/4. So we kind of like, after one cycle, we are finishing 4 instructions. In other words, one instruction takes only 1/4 if you're doing that. And then if you keep doing this for like 8, then we have 1/8 and so on and so forth. So essentially think about this as kind of like pipelining in the kind of like vertical direction instead of the horizontal direction that we were proposing before. Okay. So if you actually look into this is part of something bigger, and that's just generally like parallelism that we are using a lot in computer architecture. In fact, we have a bunch of different layers of parallelism. We have bit level parallelism, we have instruction level parallelism, ILP, we have data level parallelism, task level parallelism, and these are kind of like 4 levels of parallelism that we can do. For now, we are focusing mainly on this one. Later on, we're going to actually talk about these others as well. And then this bit level parallelism is actually when we are using 32 bits, for example, registers. If you think about this, an alternative to, for example, something like a 32-bit register was 1-bit register, right? So the difference between adding 2 32-bit values together versus adding 2 1-bit values together is exactly this bit level parallelism. So bit level parallelism, we are actually using it naturally because we are using larger data sets in larger registers and so on and so forth. Well, let's focus more now on this instruction level parallelism. And later I'm going to discuss these data level and task level parallelism as well when we are talking about multi-core systems. So let's see what this ILP can give us, okay? So ILP, basically, in order to have multiple instructions per stage, we're going to have this thing called SuperScalar processor. So scalar processor was this processor that we talked about in the class, which we kind of like have pipeline stages, and each stage gets 1 instruction at a time. And then we kind of execute this, and then this one goes here, and this one goes here, and so on and so forth, right? This was a scalar processor, okay? So now SuperScalar processor is this concept that basically says that we can issue or run multiple instructions simultaneously at each stage, okay? So for example, if I say this is a 4 issue, for example, SuperScalar, it means that I can, for example, fetch 4 instructions at a time, decode 4 instructions at a time. I'm going to talk about what is exactly an issue, but for now, for example, assume this. So if I, for example, have a 5-stage pipeline with 4 parallel lines, effectively I have 4 instructions and 5 stages of pipeline. Effectively, I'm running 20 instructions. So there are 20 different, completely separate instructions inside my pipelines. They're all running and switching at the same time. Okay, this is how we're going to get to a significant, speed up. All right. So how do we actually do this? I'm kind of like showing you a very simple design of a SuperScalar. This is just a 2-issue SuperScalar. That is like we run 2 instructions, we fetch 2 instructions, and doing everything. So as you can see here, I'm adding these kind of new red lines. So first of all, this is the same old pipeline stage. So this is one stage. Let me show you this way. This is 1 stage, 1 stage, 1 stage, 1 stage. So this is our fetch, decode, execute, memory, and write back. This is our PC. Essentially, what I'm showing here is my instruction memory and branch predictor, and this is kind of like the design that decides whether the branch predictor should be taken or not taken. This is a comparator for these two. This is the register file, ALU, data memory, and all those things. So the black ones are what we had before. What is new is these red ones that I'm showing here. So what are we adding here? Okay, so as you can see, we are kind of trying to double everything. Okay, so for example, as you can see, the very first thing I need to do is essentially fetching two instructions at the same time. Okay, so I'm fetching two instructions at the same time by basically adding two kind of lines out of two lines out of my instruction memory, right? And then these two instruction now goes to the two register file, and as you can see, my register file is actually getting two set of RS. Okay, so this is, for example, RS11, and then this is RS12, and then this the other one, this set, this red set here is RS121 and RS22. Okay, so 1 and 2 this indices, it means that the instruction, 1 and 2 is the regular RS1 and RS2 that we had before. Okay, so basically what we are doing here is that we are kind of trying to replicate things as much as we can. The important thing is that not everything can be replicated. Why? Because of the additional cost that it comes with it, that doesn't make any sense, and also because of the consistency issue. So for example, I cannot just simply double my memory, because instructions have impact on each other, and we cannot just say, okay, I have one memory for one instruction and another separate memory for the other instruction. Because what if, for example, these two instructions use the same address? Where are we going to store that? What if the instruction wants to read each other's addresses, right? So we cannot really replicate our instruction, our memory. So we cannot replicate the data, memory data cache, we cannot replicate the register file, and we cannot replicate the instruction cache. But everything else we can replicate. And another nice thing that we can do to replicate is that we can add more input and outputs to each of these. So for example, as you can see here, we are adding two more inputs to our register file. We are adding two more ports to the register file. We are adding two more ports to our instruction memory. So we are basically kind of replicating not the entire structure, but actually the inputs and output ports. And that's one thing that we can do. But we cannot just simply kind of duplicate our memories, because memories cannot be duplicated. There is only one memory that needs to be coherent, right? So kind of like continuing this story of like how we can replicate things. If you actually look into the PC, you will see that we don't need to replicate two PCs. Again, PC is just one register to always kind of show you where you are in your program. Instead, what you can do is that you can always, instead of fetching one instruction, fetching two consecutive instructions. Remember, we told you that we always have PC and PC+4. So what you can do is that instead of like going to the PC and bringing one instruction from instruction memory, this way you can bring two instructions. So you can bring both PC and PC+4. Okay. So here we're basically using one PC, which is like, for example, let's say my PC is now equal to 0x100, okay? So what I can do is that instead of just reading the 4 bytes from 100 to 103, I can read 8 bytes. I can read 100 and 103. I call this instruction 1. I will also do 104 to 107, and I call this instruction 2. Okay, so I basically, by just using one index, I'm reading two things, right? So this way, I don't need to replicate this kind of like PC. I just create two output ports from my instruction cache, as you can see here. Okay. For my register file, as I said, basically I'm creating two new read ports and two outputs. So this red one is a new read port, and these two is basically two outputs. The reason that this is two, because if you remember, we had RS1 and RS2. So essentially, if I want to read two instructions at the same time, I need a pair of RS1 and RS2 for one instruction. I need another RS1 and RS2 for another instruction. Okay, so two pairs. The only thing to keep in mind is that generally adding these read ports is very expensive. Okay, sorry about that. The phone rang, so I had to pause the video. So let's continue. So as I said, this is expensive in terms of adding. Expensive, by expensive I mean expensive in terms of area and power. but it's very beneficial in terms of performance because now I can run two things at the same time. And then as you can see, what we are basically doing in addition to all these things that we do in the fetch and decode is that during the execution, what we can do is we can add an extra ALU unit so that we can then run two parallel instructions at the same time, right? And then what we can do is, for example, we can use one of these ALUs for a store one BEQ type instructions, a simpler one, and then another one for more elaborate ALU operations. Because you technically don't run two BEQ at the same time or do two stores at the same time, but you can, for example, technically write two R type instructions at the same time. So what you can do is see. Notability keeps getting. All right. So this ALU basically is the additional thing that we are adding here. That basically this instruction one can go through this route, the other one can go through this route. One of them can be also connected to the memory. The other one doesn't need to necessarily be connected to the memory. Why? Because we cannot really have two instructions to support memory. Okay, so we can only have one instruction that's written to the memory. So like based on, and then the rest of it is just basically for write back. The last thing that we need to add is kind of like a write data, a second port to the register file to write data. Okay, this is really all we need to do in order to kind of do this two issue SuperScalar processor. We are adding an extra read port for our instruction memory, a read port for our register file, an output port for our register file, a new ALU, and then basically a wiring, and then new write data to the register file. The limitation here is that I cannot have two store word or one store word, one load word, because my memory cannot be duplicated, so I cannot really have two ports. Alternatively, I can have two ports to my memory, but usually I don't want to do that, so I typically just have one port for the memory. But technically, you could have like two ports for your memory as well, and in that case you can do everything twice. Okay, so let me see with this how would things change. Okay, so the ideal scenario in this case would be that I'm going to get IPC equal to n, or in other words CPI equal to 1 over n. For example, consider a scenario like this, that I have load word x1 for the x0, add x4, x3, x2. Then another two instruction would be like a sub and an add-I. Another two instruction would be a store and add-I. Okay. So what I can do is that, for example, if my PC is kind of like pointing to here, as I said, my PC, instead of just reading one instruction, which was this originally, and now I can read two instructions at the same time. So my IM is kind of like there are two ports. Both of them goes into the register file. Both of them goes to the ALU. Maybe one of them use DM, the other one doesn't, and then both of them goes to the register file, and boom, we have what we want, right? So at the end of this cycle, I finish both of these instructions, okay? And then same thing happens, right? So basically load and add, load and add, and load and add, load and add, and so on, load and add. And then for the second group, sub and add-I. And then basically this goes here, 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 here. So at this point we have the sub and add-I. And the same story for these two, like store word and add-I. Right? So at the end of this cycle, I'm actually finishing all 6 instructions. As you can see, this is twice as fast as if I had just one instruction at the time. Right? And this is, of course, the ideal scenario. There are a whole bunch of problems that we're going to see in the system. So let's see, what are those? So the first thing is, you might ask yourself, what about dependencies, right? So what can we do in order, for example, to have things such as, a scenario like this where we need to kind of read two instruction. In this case, this is not a big issue, but for example, what if we have something like this, that RS is on this side, and then let's actually use the X3, let's say X3, X2, X1, and then here we have, let's say, sub, and then have X4, X3, and maybe X0, something like this, right? As you can see here, what we have, like before, we have a raw data hazard. We are writing to this previous instruction, and now we are reading from here. And in the past, we showed that this can be fixed with forwarding and all those tricks that we are using. But considering a scenario like this where we are kind of like we want to issue both of these instructions at the same time, then our forwarding would be very, very complex, because we essentially need to forward, for example, from this line to this line, or from here to here. So the very, very complex things needs to be done, which is not very simple. And then checking would be even harder. So probably what you can do to kind of like fix this issue is maybe not reading two instructions at the same time. So for example, if you cannot really fill your two stages because of the dependency, you can just go back to the original one at a time. So kind of like you first feed this, and you keep the other one empty, then you kind of like feed this, and maybe if you can run another one, then great. Otherwise, you keep the pipeline empty. So basically, what used to be kind of like add sub together, and maybe like next cycle load, and I don't know, add I together. Now I basically just do add and nothing, and then do maybe sub or load together, and then maybe add I and the next instruction or nothing, something like that I can do, right? But I cannot like issue these two if there's a dependency between these two instructions, right? And then it's really hard to kind of fix that dependency if you want to kind of like forward from this instruction to this instruction, okay? But for example, if I do something like this, then I can forward this into next cycle, and then I can basically forward from here to here. But even then, the forwarding would be very expensive. Why? Because now I need to kind of forward two ways, right? So basically, I'm showing you here. Basically, what I need to do is that I need to forward from here to here, right? That's one regular forwarding that we had before. But now I also need to forward from here to here. So basically two forwarding, from one lane to another lane, and then another one from like two lanes next to each other. So forwarding becomes more complex. It's doable, but it's just more complex, okay? But the problem is, like, if you for two, it's kind of manageable, right? So I can kind of like figure out things. But what if we have like 4-issue processor or 8-issue processor, right? Then we need to check all the pairings in order to see if we can kind of run things at the same time or not. For example, if you have something like source 1 and source 2 of add, if we have 2-issue, we basically just need to check these sources with this destination and this destination with these sources. But now if you have like a 4-issue instruction, right? If you want to issue 4 instructions at a time, I need to check every 4 pairs together. So I need to check this one with this one, then this one. Then I need to check this one with this one, and this one. So for every 4, I need to check 3. So I'm gonna have 12 checks for a 4-issue, and then the probability that there is some form of dependency between these instructions becomes significantly high. Okay, because for example, if the destination of this instruction, for example, is being used of this instruction, then I cannot issue this one and this one in the same cycle, right? I need to kind of like create at least a cycle difference between the two, right? So essentially, kind of looking at the superscalar, we kind of have this sort of trade-offs, right? So we're gonna achieve higher IPC, right? at least in paper, because we can kind of like, if we can issue multiple instructions at the same time, then we can run all of them in parallel. The problem though is that it's significantly more complex to actually issue these, because we have to check lots of dependencies, because every single source pairs needs to now be compared with a destination register. There is much more hardware required for forwarding, because now I need to forward from one lane to not all the other lanes. And then I need to kind of like, add these extra things for fixing all those things. Okay. So kind of in short, SuperScalar is helpful, but by itself is not the best solution. But it's kind of a step in the right direction. Okay. So it's kind of like, the problem that it's good but not it's the ideal scenario is that, because of all these dependencies and stalls, we never actually really achieve this IPC equal to n. So as I told you, if I have an n issue pipeline register, I'm expecting to have IPC equal to n because I can finish n instruction every cycle. In reality, this number is much smaller than n. The reason for this is all these kind of dependencies. So every two might have a dependency. Okay. So to kind of summarize, scalar processors are limited to IPC equal to 1. So everything that we discussed from week 1 to last week was basically, at best, we can achieve IPC 1. But then we can introduce what we call instruction level polynomial, in other words, superscalar, which in theory can achieve much higher IPC, so IPC more than 1. But this kind of, in order fetching and then the kind of dependency between instruction and the fact that we cannot really make the instruction independent from each other, cause all of these headaches and problems of checking whether there is a raw data hazard or not. And in other words, basically means that I cannot really fill all of my pipeline stages with data that I want. Okay. And in other words, this IPC more than 1 is really more than, it's just basically good in paper, but it's not really feasible in real world. Okay. So how do we fix this? We fix this with this idea of what we call out of order execution. Okay. So so I'm going to kind of like discuss the detailed implementation of out of order execution in the next class, but I'm going to like basically talk about the basics and the motivation behind it, and so that we can then jump into the actual implementation in the next lecture. Okay, so as I said, the kind of status quo is that we have superscalars, right? For example, n is equal to 2 or n equals to 4. We have pipelining, forwarding, branch prediction. We have everything that we want. Ideally, we want to achieve IPC equal to n with very small CT. And then we want to have kind of like have minimal overhead due to raw data hazards and so on and so forth. And we have a very accurate branch prediction as well, with less than, with only 1 cycle miss penalty. So these are things that we have. And what we want to achieve is basically this kind of promise here. And as I told you in the last few slides, this is not achievable in most cases because there's lots of dependencies between instructions. So we want to fix this issue. If I can fix this issue, everything else seems to be good. And in that case, I can just basically have a very fast processor. Okay, so let's see how we can achieve this. Essentially, we can achieve this with what we call, out of order execution and fixing these hazards. So let's see how we are doing this. Let me pause for a second, and then I'll be back. Short pause, coming back. So as I said, the biggest bottleneck in superscalar processors is this fact that we cannot really fill all the pipeline stages with all the instructions due to the dependencies and hazards. One thing to mention is that compilers can help to reduce this. So for example, if you have a 2-issue kind of like superscalar, if the compiler can somehow reorder these instructions such that these two are independent from each other, these two are independent, these two are independent, you can always fill our pipeline, but compilers can only help in a limited fashion because compiler cannot really kind of like search through the entire program and find the independent instructions. So essentially, we need a much more efficient solution in order to fix this issue. So we fix this issue with what we call out of order execution. And the basic idea of out of order execution is this, is that if we want to really kind of fill our processors, our pipeline processors with instructions, what we can do is that we can find independent instructions and then put these instructions into the pipelines, right? So for example, if I have like a large window of instructions, right? If I want to pick two at a time, I can always, like, for example, pick this first one. And then what I will do is that I will check if the next one is independent from the so on, then I'll select these two. If, for example, this one doesn't work, I can check this one. If this one doesn't work either, then I can check this one. So I can continue checking this, right? And then I finally will find something that these two can then go together into the pipeline. And then the next time I can pick these two and then so on and so forth, right? The key idea here is that since I'm doing this in hardware, I'm going to explain a mechanism for doing it very efficiently. If this kind of window of searching is large enough, then effectively I can always find two instructions to feed it into my pipeline. And then if, for example, if n is much more than 2, if, for example, it's 4 or 8 or so on and so forth, I can basically kind of continue making this window larger and larger until I can find 4 or 8 instructions that are always independent from each other. And then if I have enough instructions, if my, like, I'm talking about millions of instructions, then finding 8 at a time is not that big of a deal. Okay, so in other words, I can technically get back to IPC equal to n. Of course, I can never reach really to equal to n because there are a whole bunch of issues that we always need to fix. But I can get really close to IPC equal to n for an in-issue processor if I have this kind of mechanism to do out of order execution. Okay, so how do we actually do that? There are lots of questions that come into the mind that, okay, I'm kind of saying this very kind of casually and it's as if it's not a big deal, but there are a whole bunch of problems that we need to figure out. So first of all, how do you know that, how these instructions are kind of independent? First of all, how do we actually find this? And then the second problem is that in the process of kind of reordering the instructions, would we create more problems or new problems? For example, if you remember when we kind of moved from single cycle design to pipeline design, what we had was essentially we had this issue of for example, a single cycle was like one instruction at a time. When we do the pipelining, the first issue that we had was this raw data hazards between them. So pipelining helped us in order to improve the performance, but we created a new problem, which was the hazards problem, right? And then we kind of like spent a lot of time fixing that issue. So now the question is, are we going to create new problems by out of order execution? And then of course you will have all these questions about what will happen to hazards. Are we going to raw data hazards? What about branches? And all those things. Are there going to be even new hazards? So I'm going to explain all those things and I'm going to explain them next week. But today I want to kind of give you more of like an overview of how we do this. So let's continue. So essentially we're going to have these main 3 problems and we're going to talk about this in this week, in this lecture and next lecture. The first thing that we're going to have is we need to kind of like, need a mechanism for tracking instruction. By tracking, I mean, we need to know which instruction is ready. And by ready, it means that it can go inside my kind of like, execution pipeline stages, right? Another thing that we need to do is that we need to kind of like get rid of the hazards. Given that we are kind of doing this out of order and now we have kind of like a superscalar machine, we need to figure out a way to kind of removing hazards. And one thing we will see is that not only we need to kind of removing the old raw data data hazards, we will see that we start going to create new data hazards. We're going to have write after write and write after read data hazards. If you remember, we said that in order processors, these are not an issue, but for out of order processors, this is going to be an issue. And then we're going to have even more hazards, things like load store that I'm going to talk about it. And finally, when we have something like a branch misprediction that we were flushing, now that we are doing things out of order, and we're going to have even more problems, okay? We're going to have the problem of figuring out which instruction was which and how do we actually kind of get rid of this. All right, let me quickly talk about this last one and then giving you a new concept called retire. And then I'm going to pause this video and then the rest of it, we can talk about it on Thursday. All right. So this is basically the idea of out of order execution. We're still going to have kind of like our kind of different stages. We call them fetch, decode, execute, complete, and retire. I'm going to talk about why we named them this way, but it's kind of like, you know, the key idea here is that, you know, we're not going to have everything out of order, okay? We're going to just do the execution basically out of order, but then we're going to have what we call the retire stage that I'm going to explain, and we're going to make that retire in order. So essentially the idea here is that we're going to fetch and decode instructions still in order, because that part we don't need to be worried about dependency and so on. Dependency starts, if you remember, starts here at the decode when we are actually reading the registers. So that part can be happening out of order. That's where the out of order execution come into the play. And then finally, we go back to the in order retirement, which means that we kind of like write the data back to our systems in an in order fashion. The reason for that I'm going to explain is shorter. Okay, so basically, essentially, when we're talking about out of order execution, doesn't mean that everything happens out of order. Most things actually indeed still happen in order, including fetching and decoding. But the execution and then kind of things that happens during the execution actually is a part that is happening out of order. Okay, so let's see how. So let's talk about kind of like pipeline recovery. Let's kind of like talk about this problem a little bit first, because this gives you a little bit of idea of what are sort of problems that we're dealing with out of order execution. Then I'm going to explain why we need to retire in order, and then I'm going to finish the lecture today. All right. So let's say we have kind of sequence of instruction like this: I1, I2, I3, I4, and this is kind of the ordering. So the I1 goes first, I2, and so on. So okay. So let's actually look into the pipeline and then also look into the instructions that are done, okay, that's left the pipeline and completed. Okay, so let's, for example, we have something like this, that we have an in order processor that basically goes like this, okay, goes from top to bottom. And then in that case, for example, let's say that we fetch this and then fetch this, then this, and so on. So okay, so we fetch, decode, execute, so on. Let's say we look at this snapshot of the processor where essentially, so I1 is finished, I2 is finished, I3 is finished, and now we have I4, I5, I6, and I7, for example, in the pipeline, right? So this is kind of like, you know, if I want to show it this way, this would be fetch, decode, execute, memory, write back. Then this one would be fetch, decode, execute, memory, write back, and then this one, and then so on and so forth. So I'm kind of like looking at somewhere in the middle here, where I1, I2, and I3 are finished, and I have I4, I5, I6, and I7 in the pipeline. Okay. So now let's, for example, that this I4 instruction was a branch instruction. Okay. And in that case, let's say, for example, this was a branch that's supposed to be taken, but we predicted not taken. Okay, so if we predicted not taken, then what we would do, if you remember, was basically we're gonna, you know, fetch I5, I6, and I7. And then at some point, we're going to realize, let's say, for example, at the mem stage, we're going to realize that we made a mistake. And then let's say our branch will resolve at the mem stage. So in that case, I need to flush I5, I6, and I7. And then let's say the correct instruction has to be, I don't know, I8 or I9 or something. Let's say, for example, it's I8. So we kind of like, you know, continue with I8. So this is, for example, a branch from here to here. What we should do is that we shouldn't execute these instructions. So these has to be flushed, okay? And then as you can see here, as long as we are kind of doing this in order, we don't have any issue, right? So I1, I2, I3 is already completed, no issue. I4 is in the pipeline. We fetch I5, 6, and 7. We realize that we made a problem, we made a mistake. We flush them out of my processor, and then we continue with I8 and we're good, right? So these are all the things that we discussed extensively in the past 2 weeks or so. Right? So far so good, no issue. But now let's talk about out of order execution. And then this is where things get interesting, okay? So consider the same example, but this time, for example, say that, okay, we are kind of like doing it in this direction. And then we, for example, want to do I2, I1, I2, I3, and so on. But for example, when we are kind of doing 4 issue or 2 issue, we realize that, for example, I3 cannot go with I4. So for example, we want to run I3, and we realize that I3 cannot go with I4, cannot go with I5, cannot go with I6, because, for example, 4 is dependent to 3, 5 is dependent to 4, and 6 is dependent to 5. But for example, 7 is actually independent from these. I'm making up numbers and examples, right? So don't, I mean, there's no reasoning behind these things that I'm saying. It's just I'm making arbitrary assumptions here. So basically, the assumption that I'm making here is that I7 is actually independent from all these previous instructions, okay? So what will happen is that, for example, I can run the pipelines like this. So I can do I1, I2 in one stage, and then I can do maybe I3 and I7 in another stage. This is, for example, a 2-issue pipeline or something like that, okay? And then in that case, I can then run things, okay? And then what will happen is that the important observation here is that since I'm kind of issuing this I7 even before I6, I5, and I4, there will be a scenario where I7 is essentially completed before I4, I5, I6, right? So since I'm kind of like putting this I7 before even putting I4 or I5, then obviously I7 will finish before I4 and I5, right? So the list of completed instruction I7 will be there, while I4, I3, I5, and I6 is still there, okay? So now going back to the same example here is that if this I4 is a branch instruction that's supposed to be taken and go to I8, let's see what happens here. So we're going to have I4 and we're going to realize that, oops, this is a branch, and now we have realized that this should be taken. What should we do? So the previous approach, we're saying that, okay, everything has to be flushed, right? So all I5, I6, I7 has to be flushed. But let's see what happens here. So as you can see here, basically, we're going to have I3, I5, and I6 in the pipeline. And out of this, I6 and I5 should be flushed. I3 actually shouldn't be flushed because I3 is before I4, but let's say I3 is also we decide to flush, okay? This is kind of like a performance issue, but it's not a big deal. Let's say I can flush I3 as well. But the bigger problem is that even if I can flush all these 3, there's going to be this instruction, this I7 instruction, which is already completed. It's already left the pipeline, right? And even if I kind of like, execute I8, and I already flushed these things, since I7 already completed, already left the pipeline, there is no way of kind of recovering this, okay? Because this is already written to the memory or write back. I have no idea what instruction this was. So there's no way of kind of flushing this. And this is a big problem because in real system, this should have been I1, I2, I3, I4, and then should have kind of jumped all these instructions and then kind of continue this. So I should never execute I5, I6, and I7. But with this, I'm showing that I'm actually not only execute I7, but I actually write the data that's created by I7 and write it into the register file or memory. Okay, so again, why this is an issue here and not an issue in order? Because in order, we always kind of like make sure that we are kind of executing instruction in this format. We never run I7 before 6 or 4, but in out of order, anything is possible. In other words, there's possibility that I7 actually happens before I4. As a result, by the time that we realize that we made a mistake with the branch, I7 is already executed, so it's too late to flush that instruction. Okay. So how do we fix this issue of there might be, you know, kind of what we call the younger instruction or future instruction that runs before a jump or a branch, but in reality, they should have never been executed. Okay, how do we fix this issue? We fix this issue by adding this a notion of what we call retire. Okay, so essentially, we're going to create this two-step thing, which in one case we call this complete, and in another case we call this retire. So essentially we're going to differentiate between what we call a completion and what we call a retire. Okay, so if we kind of like, you know, complete things but don't retire things, then if a flush happens, we can just flush everything that is completed, but we cannot flush things that are retired. So let's see how we actually, what is the difference between a complete stage and a retire stage. So in order to understand what does it mean for an instruction to finish, and then what does it mean for instruction to kind of retire versus what does it mean to complete, we have to kind of like think about kind of life cycle of the instruction. If you remember, the life cycle of instruction was like this, that we kind of fetch, decode, execute, and then we kind of do memory and write back. Okay, just during the memory or write back or both, what we are doing is that we are saving the data generated by this instruction into some kind of permanent storage unit, either the register file or the memory, right? So when the instruction is finished, the instruction is finished basically by updating the memory or updating the write back, or this is a control flow instruction, it would be updating the PC. Either of these three, and these are all registers, so it's basically have a, like, you know, lasting impacts. They're always going to be there. Okay, so basically finishing in our kind of methodology means that we either write things to the register file, or we are writing things to the memory, or we are updating things to the PC. Okay, when we are saying things have finished, it means that one of these three or all of these three is happening. Okay, and then when the data is written to any of these, then it's already too late to flush things, because we have no idea where this data has been written. There's no way of kind of tracking where this has been written. So there's no way to kind of find that data back. Okay, so what we need to do, and then the idea of retire versus complete, is that in complete we don't write to these things, we just keep them in some temporary buffer, and then only we write to these kind of permanent things when things are safe to do. That's, for this part we call this complete, and this part that we write to the, you know, these things that kind of look to permanent things, we call this retire. So things first complete, then retire, and this way we can say that you know, the instruction is finished. By the way, before some people call retire, some people call commit. So if you hear that some says commit is the same as retire, there's the same words, different books and different kind of people use different words. In this class, we just stick to the retire, so we don't use the word commit. But commit and retire are the same thing. All right, so going back, the problem, as I said, is that for instruction to finish, it has to write its data to some form of kind of permanent data memory or register. So either register file or data memory or the PC, one of these three registers or memory. In order to kind of help us to kind of flush things, what we need to do is kind of like differentiating between the data that is ready to be written versus actually writing it to those stages. Okay, so when the data is ready, we said that this is complete. Instead of writing it to these permanent buffers, to these permanent memories, we write it into some temporary buffers. We call that the complete stage. And then the step that we are actually writing it to this kind of like permanent storage units, we call that the retire. Okay, So in order to kind of like, have this ability of recovery, then we kind of like using this complete versus retire. Okay, so we basically gonna have this fundamental idea that we're gonna allow instruction to complete out of order. Okay, but we're gonna retire them in order. In other words, we're gonna write things permanently into my memory or PC or register file the same way that we were doing it in order processors. And we're going to do things in order. Okay, so basically, to summarize, we complete out of order, but we retire in order. Okay, and then one thing I want to mention is that we call this register file, memory, or PC architectural state. So remember, we had microarchitecture and architecture. Okay, the difference between architecture and microarchitecture is that microarchitecture is the unit behind the architecture that is invisible to the software developers and the operating system. Okay, the architecture layer is what is visible to the software developer and the operating system. So for example, if you remember, all of our register X0 to X31, these were kind of accessible by the assembly code. That's why they're part of the architectural. Memory and PC was also visible by the assembly. That's why, again, they are part of the architectural. But your internals of your data path or controller was not visible to the software developer. That's why they're part of your macro architecture. Okay, so in other words, again, to repeat what I said, we are basically proposing this idea of differentiating between what we call a complete and a retire. So we let the instruction goes into the execution stage, do whatever they want, and let them complete out of order. So complete happens out of order. But we're going to retire, which means that we're going to write into this what we call architectural stage, in other words, registers and memories, only in order. So basically, we retire I1 first, then we retire I2, then we retire I3, and so on and so forth. We never retire I3 before I2 or I3 before I1. Okay. So why this would work and how this is actually going to help our problem? So basically, consider this scenario like this. This was the problem, right? So the I7 was the problem. So as you can see, I'm calling this complete. So I'm letting these things complete, and it kind of sits into this buffer. But then I'm going to have this additional thing called retire. And then here, I'm going to retire in order. Okay. So in other words, I'm going to let I1 retire, because I1 is the first instruction, it can retire. I'm going to let I2 also retire. So basically from complete, I'm going to get rid of this and put it here. I'm going to get rid of this I2 and then put it here. But then when it comes to I7, I'm going to check whether previous instruction before I7, all of them have been retired or not. If the answer to that is no, then I'm not going to retire I7. So I7 going to stay in the complete stage, but it's never going to go to the retire stage. So now what happens is that now when I'm flushing things, not only I'm flushing the pipeline, I'm also going to flush everything that is in the complete stage. I'm not going to flush things in the retire, but I'm going to flush the entire pipeline and the entire complete buffer. Okay, and in this case, you see that we actually not going to have the problem that we had before, right? Because I7, although it's completed, but it's just never actually reaching to the kind of the permanent storage unit. Okay, so this is how we actually going to fix this issue. All right. So how do we actually implement this retire? That's the last thing I want to show you. So we basically need this additional storage units, this buffer that kind of sits between the final results of the pipeline and then what we call the retire. So basically, we need something at the kind of like this, the write back stage to kind of store these things temporarily. All right. So we need to add this buffer storage, and we also, of course, need the mechanism to kind of follow what is the last instruction that has been retired. I need a mechanism to know that whether I'm allowed to kind of retire this I7 or not. So I need to kind of keep track of what is the last thing that has been retired, such that I can know whether I7 is allowed to be retired or not. Okay, so I need these two things. Okay, and in order to achieve this, this is what we are proposing. This is what we call a reorder buffer. So an ROB or reorder buffer. So reorder buffer is basically this buffer, this table that holds the completed instructions. Okay. And then it has actually this pointer that basically it retires instruction only if that all instructions before that is already retired. So we only retire instruction if all of the instructions before it are already retired. So basically, like, examples of I1, I2, I3 all the way, we're going to retire I1, we're going to retire I2, we're going to retire I3. But for example, if we have 5, we're not going to retire 5 until 4 arrives. Once 4 arrives, we retire 4, and then we retire 5, and then we continue. Okay, so the retire always happens in order. Completes can be happening in any sort of order that they want. All right. Basically, this is how we're going to show this. As I said, we're going to fetch and decode in order. We're going to let things to kind of execute out of order. So, and then we're going to have this complete stage, which is this kind of like, temporary buffer. And then we're going to reorder things out of order. In order. Okay, so for example, let's say we have something like this, then this is our reorder buffer, this is our raw. And then let's say, for example, now we have I1, I3, I4, and I6 completed. These are our completed instructions. Okay. So we typically, in order to kind of, implement this, we have to kind of like a table like this. And then we're going to have a pointer, which we usually call head of ROB. This basically shows where this last instruction has been retired. When the instruction that is completed is at the head of the ROB, then we are fine to kind of retire this instruction. Okay, so we're going to retire this instruction. Then we're going to move the ROB one step down. Okay, this is like a stack pointer, basically goes one step down. And then here we see that, we are waiting for this instruction. This instruction hasn't been arrived. As a result, I cannot retire this, I cannot retire this, I cannot retire this, I cannot retire this. Okay, so these are staying in my reorder buffer until this instruction arrives. After some point, so that's what I'm saying, so we cannot really retire this until I2 arrives. So we wait and wait and wait. And then at some point, this I2 will arrive. And that's when we can kind of, retire this instruction. And then we can retire all the other instructions. Of course, there will be a question of how many instructions can be retired. That's the design of the processor. If you have an n-issue processor, then you can retire up to n of those at the same time. So for example, if this is a 2-issue, I can retire I2 and I3 at one cycle. Then I'll retire I4 and whatever left at another cycle. Okay. So basically, and then the nice thing about this is that, for example, if it comes at that I2 was a branch instruction and it has to flush things, then all I need to do is basically just clearing out my ROB. That's all I need to do. So the flushing is basically nothing but getting rid of these completed instructions. So that's very straightforward, very simple to do, and I don't need to worry about, what will happen if there's an I7 and so on and so forth, basically, because this way I am guaranteeing that this instruction is a branch instruction. We never retire instructions after that. In other words, we are always safe to kind of like, flush things that comes after. Everything before is completely safe because branch doesn't change instruction before it. Branch always change instruction after it. So I can flush this and nothing bad happens. Okay. So what we store in the ROB, I'm going to talk about this later. There are a whole bunch of things that we need to store, and that's when we are actually talking about the implementation. We're going to talk about that. So this would be now the kind of updated design with the ROB. So as you can see, we still have our kind of I'm showing it 2-issue superscalar. Okay. But this is an out of order design because we have an ROB. So as you can see, basically this part stays the same. This register file stays the same. Everything stays the same. The only thing that changes is basically my register file is now changing. So instead of kind of writing directly to the register file, now I'm writing things to my ROB. Okay. And then basically my ROB is the one that decides when to update the register file. Okay, so basically the ROB is the one that's updating the register file. The reason that we have all these kind of like instruction here is that once a new instruction comes, I need to update my ROB and so on. I'm going to actually discuss that when we're talking about the actual implementation. All right, so this was kind of the design without the ROB. Okay, so we had all these things kind of like, going here, and then we had like kind of data path here, but this is an in-order processor. But with the ROB, we can actually now have out-of-order processing, because now we can get rid of this. We put things into this ROB, and then this ROB is actually the one that's update the register file. Okay, so hopefully this is clear enough for you, but feel free to kind of watch this and ask questions. So to kind of like summarize, we're going to have these three problems. I already discussed this to you. I'm going to kind of summarize this on Thursday as well, but then we're going to focus on these two, and then we're going to basically focus on the actual implementation of all these things together. So I'm going to give you more details of each one of these stages. All right, so this is it. We don't need participation for today, but hopefully you can watch this before we start the lecture on Thursday, because that helps you to kind of understand the reasoning behind out-of-order execution. All right, so that's it. That's it, guys. Good luck with the quiz, and then please watch this before Thursday, and then we can talk about this on Thursday. All right. Thank you.